In the previous lecture, we had discussed the solution of the Schrodinger equation, of the one dimensional Schrodinger equation in the JWKB approximation. We had written down the solutions when k square of x is positive and when k square of x is negative, and we wrote down the connection formulae, and we said that if k square of x variation is like this, so that the oscillatory solution is to the right of the turning point, this point x is equal to a is the turning point where k square of x is equal to 0. So, in this region you have exponential solutions, and in this region you have trigonometric solutions. So, these are the connection formulae: 1 over root kappa of x exponential. You must be careful for the limits. In this region x is less than a, so x to a kappa of x goes over to 2 by root kx sine of a to x. In this region x is greater than a, so it is a to x k dx plus pi by 4. This is the exponentially decaying solution. Similarly, you have the connection formula that I had written down for the exponential amplifying solutions, and on the left and the right are the JWKB solutions. Near the turning point, k is extremely small. In fact, at the turning point k square of x is 0, and the JWKB solutions are not valid. On the other hand, if I have a situation in which you have k square of x becomes negative to the right of the turning point, then we just have to reverse this, so near the vicinity of the turning point the JWKB solutions are not valid, and we will explicitly show that probably at the end of today's lecture. And on the left are oscillatory solutions. So, you have on the left side x to a, because in this region x is less than a, and in this region it is x is greater than a. So, the limits are from a to x. So, this is the exponentially decaying solution. So, 2 by under root of k sine of x to a k of x dx plus pi by 4 goes over to an exponentially decaying solution, and cosine of this thing goes over to an exponentially amplifying solution. So, with this we will now use these connection formulae to derive an eigenvalue equation, to derive an equation which will determine the eigenvalues of the problem. So, we consider, for example, v of x is equal to half m omega square x square, harmonic oscillator, something like that. So, my k square of x is equal to 2 mu by h cross square e minus half mu omega square x square. So, as I discussed in my last lecture, you will have a variation of k square of x something like this. So, we start with an exponentially decaying solution here. We hop over this turning point, let us suppose this is x is equal to a, and go to this region. Then the WKB solutions are really valid in the entire region from here to here, and then we use the correction formulae with respect to the turning point B and hop over to this region, and we will find that in this region we will have both exponentially amplifying solutions as well as exponentially decaying solutions. We will, for a bound state, an exponentially decaying solution should go over to an exponentially decaying solution. So, the coefficient of the exponentially amplifying solution will be set equal to 0, and that will lead to the eigenvalue equation. So, let us do this. So, the exponentially, this is region 1 for x less than a, x between a and b is region 2, and x greater than b is. So, these are the 3 regions in which we will discuss the WKB solutions. So, let me first write down psi 1. We will, in the first region we have an exponentially decaying solution. So, you will have, say, some constant or a by root of kappa exponential minus, here it is x is less than a. So, this is x to a kappa of x dx, kappa of x dx. So, what is the kappa? Kappa is, kappa square is equal to minus k square of x, and in this case therefore, this is equal to 2 mu by h cross square v of x minus e, because for x less than a, v of x is greater than e, and so therefore, this is the variation of k square of x, as we had discussed in our last lecture. So, this is the exponentially decaying solution. This is the exponentially decaying solution, and that is because if kappa was constant, so this will be minus e to the power of minus kappa x, and at the lower limit it will become e to the power of plus kappa x. As x goes to minus infinity, this is an exponentially decaying solution. Okay. So, we now use the connection formula that we had mentioned a minute back, and this then goes over to psi 2 a upon root k 2. This is the connection formula which I have told you without proof, but we will prove that sine of, in this region x is greater than a to x k of x, k is a function of x, but in future I will not write k of x, just k, plus pi by 4. Therefore, this solution is in this region, Now, I must look towards the turning point x is equal to b. Now, I must look towards the turning point x is equal to b, and therefore, so I should write this integral as a to x k dx plus pi by 4. This is the phase term. This I write as a to b k dx minus x to b k dx. But in order to use the connection formula, I must add pi by 4. This is the so you have here, for example, x to a k dx plus pi by 4. This goes over to an exponentially decaying solution. So, you will have x to the turning point I have denoted by b. So, x to b k dx plus pi by 4. So, here there is a pi by 4 and this is minus pi by 4. So, I have 2 pi by 4 plus pi by 4 to take care of this and plus pi by 4 to take care of this. So, let us suppose this I put equal to theta. So, this becomes pi by 2 plus theta minus integral x to b k dx plus pi by 4. Okay. Now, in the WKB solution, we have to take the sign of this expression. So, let me write it down. Sine of this will be therefore sine of the whole quantity, and that will be equal to cosine of theta minus the whole quantity x to b k dx plus pi by 4. So, my WKB solution, as we had written down, will be psi 2 will be equal to 2a by root k multiplied by this. Okay. So, this is my WKB solution. Now, this is cos of a minus b. So, cos a cos b plus sin a sin b. So, let me write this down carefully. 2a I take outside, and you will have cos theta times 1 over root k cos of, now this is very important, x to b k dx plus pi by 4 plus sin theta and sine of the entire quantity. I hope this can fit inside this, sine of integral x to b k dx plus pi by 4. Okay. Now, therefore, I have obtained the solutions in this region, and here k of x is 0. So, these solutions are really, sorry, there is a 1 over root factor here. So, I have now the solutions here, and now I must use the connection formulae to go from here to here, and I have those connection formulae. The sine term x to a plus pi by 4 goes over to an exponentially decaying solution, and the cos term goes over to an exponentially amplifying solution. So, therefore, the coefficient of the cos term must be 0, otherwise the wave function will blow up for x greater than b. Once again, if I have a cosine term in this region, then that will go over to an exponentially amplifying solution. So, therefore, that will not correspond to a bound state problem, and so therefore, the coefficient of the cosine term must be 0. So, therefore, this term must be 0. So, we must have cos theta. So, let me write it down, that for the solution to be exponentially, to be well behaved, that is, it should not go to infinity, the coefficient of the exponentially amplifying term must be 0, and therefore, cos theta must be 0. because it is this term which goes over to an exponentially amplifying solution. This term goes over to an exponentially decaying solution. So, therefore, this cannot happen for a bound state. So, therefore, cos theta must be 0. So, this implies theta is equal to n plus half pi, where n is equal to 0, 1, 2, 3, etc. And what is my theta? Theta is equal to a to b k dx. So, theta is equal to integral from the two turning points a to b k x dx must be equal to n plus half pi. This is a very important result that we have derived. This is the eigenvalue equation, the equation which determines the eigenvalues of the problem. I will consider a few examples now. So, example 1, I have the till now our analysis was general, in the sense it could be an arbitrary variation of v of x as long as it is smoothly varying, so that our WKB approximation is valid. So, we now consider our linear harmonic oscillator v of x is equal to half mu omega square x square. So, you have k square of x is equal to 2 mu by h cross square e minus v of x. So, e minus half mu omega square x square. So, if I take out half mu omega square outside, so this becomes 2 mu by h cross square times half mu omega square, and I write x naught square minus x square, where x naught square is equal to 2e by mu omega square. So, x naught is the classical amplitude as we have discussed in our last lecture, the classical amplitude. So, x naught is the turning point. So, this 2 cancels out and you get mu square omega square by h cross square. So, let me write down carefully that k square of x is equal to mu square omega square by h cross square x naught square minus x square, where x naught square is defined to be equal to 2e by mu omega square. This is the classical turning point where k square of x is 0, so that the kinetic energy is 0 and the total energy is potential. So, my eigenvalue condition, so the turning points are, so the k square of x variation, as you can see, it will be something like this. This will be plus x naught and this will be minus x naught. Okay. So, the eigenvalue equation will be from minus x naught to plus x naught, because those are the turning points. K of x dx is equal to n plus half pi. So, let me write the right hand side in the left hand side. So, n plus half pi is equal to k of x will be mu omega by, this is a trivial integration, but let me do it, minus x naught to plus x naught under root of x naught square minus x square dx. Since this is a even function of x, so this will be mu omega by h cross 2 times 0 to x naught under root of x naught square minus x square dx. Let me do this integral, although I know all of you will be familiar with this. I do this x is equal to x naught, say sine theta. So, dx is equal to x naught cos theta d theta. So, this will be from when x is 0. So, this is 0 when x is equal to x naught, theta is pi by 2. So, this will be x naught square. So, this will be x naught outside, and 1 minus sine square theta. So, this is cos theta, and dx is equal to x naught cos theta. So, cos square theta d theta. I hope I have done it all right. So, you can carry out this integration very because the integration will be, so therefore, n plus half pi. So, let me do it like this, so that you can see the n plus half pi is equal to 2 mu omega by h cross multiplied by x naught square. So, x naught square is 2 e by mu omega square, and this will be cos square theta. So, 1 plus cos 2 theta divided by 2 d theta. The second integral will come out to be 0. I leave it as an exercise. So, half into d theta. So, half into pi by 2. So, this will be into half into pi by 2. So, this is mu cancels out, omega cancels out. So, this will be 4e, the 4 cancels out. So, 4e by h cross omega. So, this 4 cancels out with this, pi cancels out with this. So, you get the result that the energy eigenvalues for the harmonic oscillator is n plus half h cross omega. So, we get the exact result. We had derived this by using the bracket algebra and also by solving the Schrodinger equation. So, we get the exact result, and this is fortuitous exact result. And one of the reasons is that the parabolic potential, the parabolic potential is a very smoothly varying function, So, therefore, we get very accurate results, but it is fortuitous that we get the exact results. So, this is the recipe for obtaining the eigenvalues. Let me do one more problem. Actually, we will do, this was example number 1, and we will do another two more simple problems to tell you the tricks of using the connection formulae. So, example number 2 is a linear potential. I assume a particle such that at x is equal to 0, it is infinity, and as for x greater than 0, it is equal to gamma x for x greater than 0, and is equal to infinity for x less than 0. So, it is a triangular potential, and this is my x axis and this is the v of x. Now, I assume any value of energy. So, let me assume E can never be negative. So, this is gamma x, this is the line gamma x. So, I assume E. So, where E is equal to V x, those are the turning points. So, my k square of x will be 2 mu by h cross square E minus gamma x. So, one turning point is at x is equal to 0 and the other turning point is at x is equal to E by gamma. I hope this is clear. At x is equal to E by gamma, k square of x is 0. And let me solve this. This is very simple. So, you have k of x, that is you have n plus half pi will therefore be equal to, between the two turning points, 0 to E by gamma k of x, that is under root of 2 mu by h cross square, and then E minus gamma of x raised to the power of half dx. So, this is an equation which is extremely easy to solve. So, you have 2 mu by h cross square 2 by 3 with a minus sign, because as you integrate. So, E minus gamma x raised to the power of 3 by 2, yes, with a gamma sitting in the denominator, and this will be from 0 to E by gamma. There will be a minus sign because this is a minus. So, you will get, this is a very simple integration. So, if I take gamma outside, so you will get 2 mu by h cross square, 2 mu by h cross square multiplied by 2 by 3 gamma. This is equal to, and then if you take the limits, at the lower limit it will be e to the power of 3 by 2 and that is it. I think that is it. So, this comes out to be e to the power of 3 by 2, and therefore, you will get e to the power of 3 by 2 is equal to 3 by 2 gamma h cross square by 2 mu n plus half pi. Okay. So, you can put gamma square out inside. So, you can write down h cross square gamma square by 2 mu raised to the power of 1 by 3, because this is half, multiplied by 3 by 2 n plus half pi raised to the power of 2 by 3. So, these are the energy eigenvalues. Now, let us suppose this I put equal to E0. So, you get E is equal to 3 by 2 n plus half pi whole raised to the power of 2 by 3 raised to the power E0. So, this is an analytical expression, and if you substitute the values of n equal to 0, you will find that E comes out to be the allowed energy levels comes out to be 1.7707 E0. This is for n is equal to 0. This is n is equal to 0. Then you will have 4.0. Let me write it down on a separate page. So, if you substitute n equal to 0, n equal to 1 and n equal to 2, you will get the following values. E is equal to 1.7707 E0, and this is equal to 3.6838 E0 and 5.1775 E0, and so on. This is for n is equal to 0, this is for n is equal to 0, this is for n is equal to 1, and this is for n is equal to 2. This particular problem, the linear potential that I had considered, can be solved in terms of Airy functions, or rather in terms of Bessel functions. I leave it as an exercise for those who want to do. So, you can solve it very easily with the help of Airy functions. So, if I solve that problem, then the exact values comes out to be 2.3381 E0. These are the exact, and then 4.0879 and 5.5276. So, you see that for the linear harmonic oscillator problem, we were fortunate to get very good results. But here, if you compare these two set of numbers, this and this, then the agreement is not very good. And let us look at the reason why it did not work out. Because this is because of the fact that if we look at the potential, this is the potential, the V of x is infinite here. So, from the value 0 it becomes infinite. So, there is an infinite change in the value of the potential energy. And so, therefore, WKB approximation, if you may recall, was 1 over k dk by dx is less than k. So, around this region, the WKB wave analysis is not quite right. So, how do we improve that? We start thinking like this, that we say that at this point V of x is infinite, and so therefore, the wave function must be 0. So, we think of a wave function which goes to 0 at x is equal to 0. So, you have this as the potential, and you want a WKB wave function which is 0 at x is equal to 0, and that wave function is psi of x is equal to a by root k of x sine of this point is 0. So, 0 to x k dx. Now, this solution is therefore vanishes at x is equal to 0. So, it satisfies the boundary condition at x is equal to 0. So, my turning point is at x is equal to a, let us suppose, which is equal to E by gamma. So, now I must put the argument looking towards the turning point A. So, that the argument should be from x to a k dx plus pi by 4. This should be the argument. So, I must write this so that it has a term which is equal to this. which is very simple, because 0 to x k dx is equal to 0 to a is e by gamma k dx minus x to a k dx. Then I must add pi by 4. So, I must add pi by 4. And because I have added pi by 4, so this is minus pi by 4, so I must this pi by 4. So, you will have this will become, say let us suppose this is theta. So, this is theta minus, or let me put it as phi, so that it does not. So, phi minus integral x to a k dx plus pi by 4, where what is phi? Phi is defined to be equal to integral 0 to a k dx plus pi by 4. So, therefore, therefore, my solution will be sorry. So, the wave function is psi of x is equal to a by root k sine of this thing. So, this argument is equal to so much. So, sine of, so the wave function becomes, psi of x is equal to a by root k sine of phi, this quantity, phi minus integral x to a k dx plus pi by 4. Let me put it, align this properly. Okay. Now, this then becomes, I can write it, expand the sine term. So, I get a by root k sine phi cos of x to a k dx plus pi by 4 minus a by root k cos phi sine of this term, sine of x to a k dx plus pi by 4. Now, as we know from our connection formulae, which I had written down here, that which we had written down here, that it is the sine term which goes over to the exponentially decaying solution, and cos, whose argument is x to a k dx plus pi by 4, goes over to the exponentially amplifying solution. So, this is the argument is now in the same form. So, this goes over to the exponentially amplifying solution. So, my sine phi should be 0, this should be 0, this will lead to the exponentially amplifying solution. So, for the bound state, its coefficient must be 0. So, therefore, phi must be equal to n pi. And what was my phi? Let me, we just wrote it down. Phi was equal to integral 0 to a k dx plus pi by 4. So, therefore, the eigenvalue equation condition will be 0 to a k dx is equal to n minus 1 by 4 pi. and n will of course take 1, 2, 3, etc. So, it is not n plus half pi for such a problem. If you force the wave function, if you force the wave function to vanish at the left turning point, then the eigenvalue condition slightly changes, and so therefore, you will have n minus 1 by 4 pi, and so therefore, the corresponding energy values you can immediately write down that instead of the previous result, it will be 3 by 2 n minus 1 by 4 pi raised to the power of 2 by 3 E 0. So, in my previous result it was n plus half pi. So, I must have n minus 1 by 4 pi. So, this is the difference in the result. Let me write down the if I now in this expression, if I now put, I leave this as an exercise for you, n is equal to 1, 2, 3. So, instead of n plus half pi, if you put n minus a quarter pi, then the result will come out to be equal to 2 point, this is the modified JWKB result, slightly modified JWKB result, and this will come out to be 2.3203 E 0, 4.0818, 5.5172. So, you can see now that the results are extremely good, and the only thing that we did was that at the point x is equal to 0, where the potential became extremely large, I made the wave function, I made the JWKB wave function go to 0. So, if you use the JWKB connection formulae with little bit of care, then as I said, as I showed you through this example, it can give you very extreme, very good, very accurate results, provided of course in between v of x does not vary very rapidly. So, you have to use this method with care. It is really one of the most powerful methods that is there. Let me conclude this part by mentioning that how to get the wave functions. The wave functions are a by root k of x, say something like sine of 0 to x in this particular case, where we made the wave function go to 0. And what was my k of x? K of x was equal to 2 mu by h cross square e minus gamma of x, e minus v of x. So, k of x will be the square root of that. This is k square of x. So, k of x will be. So, integral of 0 to x k of x dx will be under root of 2 mu by h cross square. This we had done before. So, integral of this quantity. So, integral from 0 to x e minus gamma of x raised to the power of half dx. So, once again it will be under root of 2 mu by h cross square minus 1 over gamma 2 by 3 e minus gamma x raised to the power of 3 by 2. And so, these limits are from 0 to x, and you will write down say 2 by 3 gamma outside under root of 2 mu by h cross square, and let me take the lower limit because there is a minus sign here. So, the lower limit is e to the power of 3 by 2 minus e minus gamma x raised to the power of 3 by 2 divided by k of x. So, divided by square root of k of x. So this will be sine of this function. So this is, let us suppose, phi. So sine of phi divided by under root of kx. So my wave function will be a by say 1 over root k. Root k will be 2 mu by h cross square raised to the power of 1 by 4 e minus gamma x raised to the power of 1 by 4 sine of 2 by 3 gamma under root of 2 mu by h cross square and e to the power of 3 by 2 minus whatever this is. You can use a small program to calculate this. But there is one point that I would like to mention, that at x is equal to e by gamma, the denominator becomes 0 and the function blows up. So similarly, I can use now the connection formulae. So write down the formula in terms of under root of kappa of x and e to the power of minus say a to x kappa of dx, and kappa is under root of 2 mu by h cross square. Now v of x minus e. So therefore gamma x minus e raised to the power of half, and you can immediately integrate it and obtain an analytical expression for the JWKB solution. So the wave functions are very easy to determine, but so this particular problem, as I mentioned to you, that the potential is like this. So this is infinity and this is 0 and this is gamma x. For this, in this region I can write down the solution in terms of Airy functions, AI functions and BI functions, which are related to the Bessel functions. So for those who have not heard about the Airy functions, let me mention that they are related to J1 by 3 functions. So in fact one can obtain the exact solutions of this problem. So the exact solutions are, this is the first energy level, this is the first eigenfunction, this is the second energy level, this is the second eigenfunction, this is the third energy level, and this is the third energy. Notice that the first wave function does not have any zeros except the 0 at the boundary. This second eigenfunction, this is the ground state wave function. First excited state has 1 0, the second excited state has 2 zeros, and the third excited state will have 3 zeros. Now using the WKB solution, the result that comes out is something like this, that we had assumed that the wave function to be the WKB wave function to be 0 at x is equal to 0. So it almost hugs the exact solution. So this is exact and JWKB for the linear potential. And notice only this is the turning point. This is the turning point, and at the turning point the WKB solution becomes infinity. But other than that, far away from the turning point, the WKB solutions are all right. So I hope I have made myself clear that given the form of case v of x, you can calculate k of x, you can integrate that and find out the approximate form of the wave function. Actually the wave function is fairly good, is in fairly good agreement with the exact wave functions, except at the turning point, because at the turning point the JWKB solution is not accurate, and in fact it goes to infinity. Let me also tell you that we had long time back discussed the exact solution for the harmonic oscillator problem. So this is, you remember that for the harmonic oscillator problem we had let me brief you that k square of x is equal to 2 mu by h cross square E minus V of x. So, E minus half mu omega square x square. So, you can write this down in terms of some dimensionless quantity. You may remember lambda minus xi square, and the eigenvalues are lambda is equal to 135 etc. So, for the fourth eigenvalue, it is 7 minus xi square. The exact functions are of course the Hermite-Gauss function, and this is actually h3 of xi e to the power of minus half xi square with some normalization constant. And one can also, I leave it as an exercise for you. It is done in our book on quantum mechanics, how to find the JWKB solution, but you can find out the JWKB solution and you will find that the WKB solution goes to infinity at the two turning points. Otherwise, it agrees quite well with the exact function. So, for the other, there is another this is probably wrong, this is probably 9 minus x square, and this is again for another eigenvalue for n is equal to 5. So, this is 11. So, this is 11, lambda is equal to 11. So, it has 5 zeros, 1, 2, 3, 4, 5. This is the fifth state, 0, 1, 2, 3, 4, 5. This is half h cross omega, 3 halves, 5 halves, 7 halves and so on. So, this is the n equal to 5 state, and n equal to 5 state will have 5 zeros, 1, 2, 3, 4, 5 zeros. This is the exact solution, and this is the JWKB solution, which agrees quite well with experiment with the exact results. So, what we have developed is a very powerful method, for solving a second order differential equation, for obtaining the wave functions and the eigenvalues for for a smoothly varying potential. Now, I will do one more example, and example 3 is for a symmetric double well potential. Now, in which you have a potential energy variation which looks like this. It is symmetric about such type of potential are of extreme importance in molecular physics and even in other areas. So, we will use the WKB method, the JWKB formalism that we have found out to solve such a problem. So, since V of x is a symmetric function of x, that is V of minus x is equal to V of x, therefore, my wave functions are either symmetric or anti-symmetric. So, either psi of minus x is equal to psi of x, or psi of minus x is equal to minus psi x. So, this is a symmetric function of x, or an anti-symmetric function of x. Now, let us suppose I assume this as the energy eigenvalue. Now, in this region, the potential energy is greater than the total energy. So, k square is negative, and if therefore k square I should write as minus kappa square, and if I take this to be a constant, then I can write the solution as e to the power of plus kappa x or e to the power of minus kappa x. Alternatively, in this region, if I assume a symmetric solution, it will be either cos hyperbolic kappa x or sin hyperbolic kappa x. So, we will either start with if we discuss the symmetric solution, we will start with the cos hyperbolic function. If I discuss the antisymmetric solution, then I must use the sin hyperbolic solution. I will consider one of them and leave the other as an exercise for you. So, with that we end this lecture, and we will continue from this point onwards in my next lecture. Thank you.